Swayam Prabha. Digital India. Educated India.
So, last part of the discussion on this liquid to solid transformation is how the solidification happens in a casting or a ingot. As you know, in the industries we pour the liquid metal, mostly alloys, into a mold, and this mold will be normally a metallic mold or even a sand mold. So, here I am going to tell you some aspects of solidification of this casting. As you know, the solidification of the alloys in a casting is much more complex than what I am going to discuss with you. For details, if you want to know, you should look at two different books. Just I am going to give you a very basic idea how things can happen. So, if I pour a liquid into a big mold, it may be metallic mold or ceramic mold like sand mold, what will happen? Immediately the liquid will come in contact with the mold wall and it starts solidifying. So, what will happen? There will be very small crystal which will form. As you understand, at the boundary or the walls there is no dearth of heterogeneous nucleation sites available, large number of heterogeneous nucleation sites available. So, therefore, these crystals will easily form and they will be very small size because of the large undercooling and also cooling rate, because the liquid which is at a very high temperature will be chilled as it is reached the walls of the container, and thus this will lead to the nucleation and the very small large number of nuclei form at the walls, and this nuclei will grow very slowly, nuclei will go they will remain very small size because it is chilled, and this zone is known as chilled zone in the casting. Now, obviously, the important aspect for the solidification to happen further is the heat transport. The heat from the liquid must get out to the mold wall to the outside. So, to do that, the crystals which will grow in the liquid must be growing in the direction such that the heat flow can be maximized. So, what will happen? This crystal which is formed on the walls as a small size, all of them will try to the liquid, but as the heat transport becomes primarily important, only the crystals which are columnar like this, they will be winning over than the others. If there is a crystal which is going like that, the heat transfer may not be happening along this axis, so it may not be the fastest one, so therefore it will die out. That is why these crystals will not stay. Okay. So, I am drawing a very small schematic picture so that you can try to see that only few crystals which are present or which are actually kind of lying in such a way that heat can pass through very easily, or they actually allow the fastest transport of the heat, they are the ones which will be growing over than the others. So, out of all so many thousands of the crystals which are present in the chill zone, only few of them will be allowed to grow, and this zone this is known as columnar zone, because the crystals here looks like columns. Now, finally, whatever liquid left over the central part of these things, okay, so they will be solidifying like equiax grains. Why? That is easy to understand also. As you have seen, I have shown you that for the equiax crystals to grow, the temperature gradient from the liquid to solid, solid to liquid must be negative. Correct. Why? Because if they require very large undercooling in the liquid. So as you know, this will, as the liquid solidifies, lot of solid will be rejected into the liquid. Because of solid rejection, the constitutional undercooling present in the central part of the ingots will be very large, and this constitutional undercooling will allow the equiax grains to grow. They do not have any problem nucleation. Why? Because of the fluid flow present in the liquid, there is a chance that some of these dendrites, or the top part of the dendrites of this columnar dendrites, will break away and reach the central part of these ingot, and then they will start the growth of these equiax crystals into the liquid. These equiax crystals will look like this. That is why they are called equiax, because they have dendrites arms of equal length. That is why they are called equiax grains. So they will be all present along in the central part of this crystal. So that is another one. Okay, you can similarly draw another one. Another one. So the central part, if I draw here, if I draw color things, that is what is shown here. Okay, so therefore this zone is known as equiax zone. So in a normal ingots, there will be 3 zones then. The chill zone, which is very near to the walls, which are large number of crystals present because of high nucleation rate but small growth rate, followed by columnar zone because of the heat transport which is required from the liquid to solid fast. That is why they will grow like columnar crystals, and in the central there will be a equiax zone. This is the in general picture, but in many cases you may not see all the zones. Many cases you will see columnar zone is present, along with chill zone the equiax zone may not be present. That depends upon how the heat transport actually happens in the mold, from the liquid to the mold wall to the outside. Okay, that depends on that, and that depends on the different alloy type also, because the conductivity of the solid will also be dictating what is the way heat is transported, the KL terms or KS terms which I have given in the equations earlier. So that actually happens, and remember this is only in types of dendrites. You can also have eutectics present along the dendrites, which is not shown here. Those eutectics also will grow as a last part of the liquid. If the alloy is basically not exactly eutectic compositions, then what will happen? There will be dendrites for eutectic present in the microstructures, and this eutectic will be solidifying at the end of it because it has the lowest melting temperature, and they will be present in the central part of the castings. So finally, this is important actually. One can actually describe a much better heat and the solid balance model for that, and that is a part of the certification courses which are available even on NPTEL for many of these cases, but we cannot discuss subtle things of these situations in a detailed manner. So with this I wind up the certification part of the course, and I will now go to the next part of this course, which is basically very large, that is the solid to solid phase transformations. As you know, the most of the phase transformations which you read in the books are solid to solid types, and there are a large number of these transformations, and we are going to discuss these transformations in detailed manner. So solid to solid transformations are basically will be happening, forming a new solid inside a old solid. Okay, that means a product phase will form, product phase which is solid will form in a parent solid phase. Depending on the mode of mechanisms of these transformations, type of what is the exact mechanism of transformation, we can divide them into 2 broad classes. One is the diffusional transformation, and other one is basically diffusionless transformation. Diffusional transformations are basically depends on the diffusion of the solids, or actually diffusion of the atomic pieces, rather let me say properly. They are the ones which will dictate the transformation and the kinetics. But there are transformations which we will discuss later part of this course which does not require diffusion of these atomic pieces. They can happen without diffusion also. They are known as a diffusionless transformations, and they actually happen because of the shear forces which are present during transformations, which we will discuss in detailed manner. So, first we will take up the diffusional transformations. As you know, there are many diffusional transformations solid to solid presents. I am going to talk about few of them in this course, but I must inform or tell you all the, basically not all, most of them present in the literature. The first one which is written here is the precipitation type. Precipitation means a formation of a new phase from an old phase, and that is what is shown here, alpha prime going to alpha plus beta, where alpha prime and alpha have the same crystal structure, but beta has a different crystal structure. Alpha prime contains more solute than the alpha. Then the important transformation in solid state which requires diffusion of this atomic pieces is eutectoid, and the transformation is this gamma going to alpha plus beta. You can also have a transformation known as ordering, where alpha, which is a disorder state, can go to order state. That also needs the movement of the atoms from one part of the crystal to the other part of the crystal. You can also have massive transformation, okay, in which there is no compositional change, only the beta goes to alpha. Or you can also have a polymorphic transformation, which is very common. Iron is the greatest example of polymorphic transformation. Iron at room temperature has a body center cubic structure, pure iron I am talking about it. Room temperature and 1 atmosphere pressure, it has a body center cubic structure. If you heat up beyond 912 degrees Celsius, it becomes phase center cubic structure. Again, if you heat beyond 1394 degrees Celsius temperature, it becomes delta, 1494 degrees Celsius, it becomes delta iron, okay. And then it melts about 1539 degrees Celsius temperature. So therefore, iron actually can transform into different type of crystal structure depending on the pressure and temperature. And this is known as polymorphic because there is no compositional change. Only thing which is changing is basically crystal structure as a function of temperature and pressure. Okay, now what are the different types of phase diagram we can attach with each of these phase transformations? Let us first talk about precipitation. Precipitation, as I told you, is like alpha prime going to alpha plus beta, and the phase diagram shown is like this eutectic type. We have been discussing this type of phase diagram quite a lot. Here you see the alpha page shows the solid solubility of beta B in alpha is temperature dependent, it keeps on decreasing like this. So therefore, we can have a precipitation type from alpha supersaturated to alpha plus beta, that is what is there. You can also have precipitation from alpha to alpha plus beta in eutectoid systems when the composition is away from the eutectoid. This is eutectoid composition, okay. But if we go away, if you have less composition than that or more composition than that, in both the cases you have precipitations of alpha or beta phase is possible depending on the type. Similarly, you can also have periodic systems in which beta phase, here you can see here this is beta, this is periodic isotherm Tp, and there is a periodic reaction here, liquid plus alpha going to beta. So this beta phase, which is a single solid solutions, can actually transform to alpha plus beta and lead to precipitation. So this is possible. Eutectoid is a classical system which is present in iron carbon system also, which we will discuss in detail, in which gamma going to transform to alpha plus beta. Eutectoid and eutectic reactions look similar. Eutectic is like this, liquid going to alpha plus beta, eutectoid is like this, gamma going to alpha plus beta. So only difference between these two reactions is the liquid in the eutectic system reaction is replaced to a solid gamma phase eutectoid systems. So anywhere you see toid word is basically correspond to solid transformations. Whenever you see a tick, eutectic, peritectic, you see the tick word, tick is present in the word, that means that transformation involves liquid phase. But the moment you see a toid in the word, that means the transformation in solid state. So eutectoid is a solid state version of the eutectic. As you see, a phase diagram looks similar, the gamma going to alpha plus beta here, and eutectic is liquid going to alpha plus beta. Now also let me show you few examples of the ordering. Okay, as you see here, alpha, which was a disorder solution, has, when you cool down, it becomes alpha prime. So that is an order phase of that. The classical system in which it is seen is the copper zinc, in which the phase diagram is shown here, the beta going to beta prime as you cool it down below about 400 degrees Celsius temperature. Beta brass basically transform in a copper zinc system. Okay, massive transformations are little new and this requires discussions, but I am just showing you the phase diagram type. As you see here, the beta can directly transform to alpha without actually transforming to alpha plus beta here. Without transforming to alpha plus beta, beta can directly go to alpha without any change of composition. Okay, you see here there is no change of composition when beta transform to alpha, and this is known as massive transformations. This is seen in many cases, this is pay-tectoid systems. You can also have such a transformation in eutectoid system like beta going to alpha, although you should have gone to alpha plus beta, but this is metastable. Remember that, because we are extending this line at a dotted line in the phase diagram that equivalent to a metastable system. So you can also have a supersaturated alpha forming out of beta. Polymorphic, as I told you, is beta going to alpha or gamma, whatever it is. Here it is when gamma going to alpha, just like pure iron I told you, gamma to alpha transformation is 912 degrees Celsius temperature, gamma is FCC and alpha is BCC in pure iron. So therefore, this transformation does not require any compositional change. This only happens in pure systems, like it can happen in zirconia also, it can happen in pure iron, you can also have it in sulfur. Sulfur has many types of polymorphs present, and these transformations are known as polymorphic because it is the same material, pure, either it is a compound or it is a metal or metallite, it is transforming from one phase to other phase as the temperature changes at a constant pressure. Iron is the classical example, and we actually use these particular aspects of the transformations of iron in the steel making or in basically physical metallurgy of steel, which we will discuss in a very detailed manner in this course itself. Okay, so now question is this, as you know there are so many solid state transformations possible, and if I want to discuss each of these things, and there is another one which I am not discussing here, which is known as spinodal decomposition. Okay, that also requires diffusion, but different types of diffusion, field diffusion, which I have discussed in the diffusion part of my course. So out of all these transformations, we will concentrate on few of them. The first one which we will concentrate is basically precipitation, because precipitation is a very important phase transformation in the metallic systems. Why? Because many of the industrially important alloys like aluminum copper alloys, aluminum copper, magnesium silicon alloys, they are actually the whole transformation depends on precipitation of the particular phase or phases. So therefore it is important that we discuss the precipitation hardening, precipitation phase transformation in detailed manner. Similarly, we will discuss eutectoid transformations as well as the little bit about the spinodal decompositions. And as a part of the eutectoid transformations, as I told you that if diffusional transformations are not possible, you can also have diffusionless transformations. So we are going to discuss martensites in the steels, as you have seen probably in the detailed syllabus of the course. So martensite transformation is also similar like a diffusionless transformation, and we are going to discuss in detailed manner about that. Now as you have seen, the precipitation is a very important phase transformation. The phase diagram which allows you to understand precipitation type, I will just take a couple of minutes to describe you that. Important aspect is that, as I showed you, if you want to have a precipitation, If you want to have precipitation hardening in a system, a phase diagram must satisfy certain things. First of all, as you see here, alpha is a solutions of B in A, and it will have a similar crystal structure as that of pure A. Whereas beta is a solutions which is B rich. Now if I have an alloy composition like this, suppose given by this, let us suppose this is a composition of the alloy X0, okay, let us write XB0, right. Now if I take this alloy and at this temperature heat it up, let us suppose this is at temperature TQ, TP, let us suppose. At the temperature, it is a single solution alpha phase in this, at this temperature. Now if I quench it, this temperature TQ, if I quench it means if I heat the alloy at this temperature TP, and then from that temperature if I drop the sample into a liquid water or liquid nitrogen, whatever, what will happen? This alpha phase will be retained at temperature TQ. Now although alpha phase is retained, but as you see here, at this temperature alpha phase contains about XB0 amount of the solute B. On the other hand, as per the phase diagram, at temperature TQ it can only contain this much amount of XBE amount of the solute, because the solid solubility of the B in the alpha phase is slowly going down. So therefore, the solid solubility at temperature Tp was very high, in fact it was this value. Now because it has got reduced, quenched to TQ, the solid solubility has reduced. So excess solute which is present, which is between these two values, must be taken out from the alpha, and this excess solute leads to formation of beta in the from the alpha. So the alpha which is quenched is known as supersaturated alpha. That is what we have written alpha prime, and this alpha prime actually transformed to alpha plus beta, where alpha will have compositions of XBE and beta will have a composition now given by this much. Okay, this is XB beta. This is obviously alpha phase composition in all the cases, correct? So this is exactly known as precipitation hardening. Now we must have a phase diagram like that in which the solid solubility of B in the alpha phase will basically change quite drastically as a function of temperature, then only. If it changes slowly, if it changes also very little, then this is not, the precipitation hardening is not possible. So only in those phase diagrams like aluminum copper, in case of magnesia aluminum oxide or some other systems, these are the two classical systems which is metallic one is ceramics, that this such kind of phase diagram exists. So aluminum copper, magnesium oxide, aluminum oxide, these are the two systems which shows precipitation hardening extensively. So we are going to discuss mostly on taking the aluminum copper systems and tell you how actually nucleation and growth happens in the next subsequent lectures.